Amoly, and the title of my presentation is Simple Method of the Post-liquefaction Settlement Analysis based on the shear wave velocity. And this is the extent topic for my thesis. And there is my great honor for me to supervise by Professor Huriye Bilsel and as well as Professor Kenji Ishihara. About the liquefied settlement, liquefied induced settlement, when saturated soil deposits are subjected to earth shaking during the earthquake, poor water pressures start to dissipate, leading to liquefaction. So, based on that, accompanied by some changes for the volume change in the sand deposits and manifested in the ground surface as a settlement, so-called as a liquefied induced settlement. So many research work on it in the post-liquefaction volumetric strain in laboratory tests in terms of relative density and maximum shear strain, such as Lee and Albaiza, Tatsuoka, Nagase and Ishihara, and etc. And all of them, produce a methodology for the estimation of the liquefaction-induced settlement based on some important parameters such as penetration tests, such as SPT value and CPT value. So for this study, we want to introduce you a methodology for determining the settlement or liquefaction-induced settlement based on the shear wave velocity versus or in terms of maximum shear strain and the factor of safety. So this is the literature review about the paper by Ishihara and Yoshimine, and this is the important parameter as you can. As you can see, the factor of safety versus the post-liquefaction volumetric strain. For starting, we want to work on the correction of the relative density because the relative density obtained from the Japanese method calculation is a little different from the ASTM method. So because of that, for the Japanese Geotechnical Society as a JGS, we consider for the evaluating E mean and E max based on this method, as you can for this one. Could you turn on one of these? This is for finding the value for the E max, E max. And we have to put the soil layer in 10 layers, and each layer we have to apply 100 impacts in 4 sides of the mold. And next. And this is for the E max. You have to pour the soil on the mold and with upward, with a constant speed upward, so fill this mold. And based on that, we want to weigh the value of the sand inside the mold. Okay, next slide. Next slide. Okay, for the correction of the relative density, based on that, we know about the value of the E mean for the Japanese method is greater than the E mean from the ASTM method. So the Ishihara et al. Introduced a curve to make a correction. And we have an important curve, the relationship between the void ratio range versus the fine content is very important for our procedure, and later on I will let you know when we use this. This is the importance of the cyclic shear strain. as you can see, when high level of the maximum shear strain, increasing the value of the volumetric post-liquefaction volumetric strain, as you can see here at the right-hand side figure. Based on this study, we work on some data from the Asahi City in Japan. As you can see, this is this area was affected by liquefaction during the 2011 earthquake. So the first we want to consider as a block sampling. Why I use this figure? It's very easy to handle in the Cypress and easy to get an undisturbed sample by this method. The other things for the method for the undisturbed soil sampling, we use the single tube and Denison and triple tube sampler, as well as the advanced method for the gel push sampler developed by Kisujiba company in Japan. So this is the way we can prepare undisturbed sample in the laboratory, and this is the way reconstitute preparation in laboratory. And this is the equipment, the cyclic triaxial test. Equipped by a device, we can measure the shear wave velocity. This is the totally different from the normal measuring the shear wave velocity as a bender element. There is no any object to go through the soil to disturb the soil, but you can see the top side make a torsional impulse, and the downside in the pedestal part. With a sensor, we can calculate transmission time, and based on that, we can find the shear wave velocity. So this is the method for the downhole. We can monitor the arrival of a wavefront based on this receiver or geophone. So this is the range of the sample in the Kisujiban company from the 5 centimeter to 30 centimeter. This is the typical cyclic triaxial test apparatus, but this is very interesting for me as well. This is the biggest cyclic triaxial apparatus I have been seen in the Kisujiban. Please turn on the video for this. 60 centimeter in diameter and 60 centimeter in height. They get a project from Australia and use calculate the liquefaction resistance. Okay, next slide. Okay, this is the typical soil profiles. We can calculate as a SPT n value and the shear wave velocity. And also, this is the important graph. As you can see, we have to put all data about the Asahi City in this graph as a relative density or corrected relative density versus shear wave velocity, but there is no any good trend we can use it. So we have to put the other important parameter as a void ratio range to this graph, and we can find the lower and upper bound, and based on that we can consider as a angle bisector as a average line through these points. And we use the soil data to verify some curves developed by Ishihara 2016. And also, this is related to the reconstitute clean sand and reconstitute silty sand. This is exactly from the shear wave velocity versus post-liquefaction volumetric strain. As the maximum shear strain is 2.5. This is the undisturbed clean sand. This is related to the undisturbed silty sand. And this is related to the curves proposed for the reconstituted silty sand and reconstituted clean sand. And this is the summarized curve we get from the chart post-liquefaction volumetric strain versus the shear wave velocity. So for the undisturbed sample at the bottom, we consider as a natural deposit, and for the upper part, 2 lines up from the clean sand and silty sand related to the artificial fields. So for calculating the factor of safety, we need a chart. So we have to use our chart as Amoly et al. 2016. We can get an average of these for finding factor of safety against liquefaction. So for this curve, we can find the upper level of this curve as a 240. For verification of our chart, we have to make a comparison between the FL, or say factor of safety from the shear wave velocity with factor of safety with n value. So we can see a good agreement between them. Now we want to introduce 2 procedures as a procedure A. When you want to calculate the post-liquefaction volumetric strain, the first you want to know about the value of fine content. With this curve, we want to find the void ratio range. And based on the void ratio range and shear wave velocity, we can find the relative density. And based on the relative density, we can find one of these. We want to select one of these curves. And based on that, for that curve, we can find the corresponding post-liquefaction volumetric strain. The procedure B, we can consider this one. One of these conditions we can select easily. Based on the shear wave velocity, we can find the volumetric strain. Based on the volumetric strain, maximum volumetric strain, we can find the corresponding volumetric strain for each layer. So for the verification, we can use some coastal line around the Tokyo Bay, and we have a 4 soil profile from the Urayasu and the Chiba area. So this is the progress of the reclamation work in Urayasu, as you can see. And the final part we consider as a soil profile, the value of the fine content, shear wave velocity, factor of safety. Based on that, we can find 2 procedures, the volumetric strain, and then we want to find the value of the settlement. So the settlement is greater than 40 centimeter. The settlement 39 is calculated by Ishihara et al. 2016, and the observed settlement between 20 centimeter and 50 centimeter. So the other things, as you can see, I don't want to take much time for this one. It's an important thing, as you can see here.
Okay. It's okay.
2 minutes.
It's okay.
Okay. The comparison between VS-based procedure and SPTN-based procedure used for computing liquefaction-induced settlement have indicated a reasonable level of the coincidence. But we have a problem for shear wave velocity. Thin liquefiable soil layer are particularly impossible to detect by VS-based procedure. So a little, we have to be careful about this drawback. And also, there is a reasonable level of the consistency between the settlement computed by VS-based procedure and also the settlement observed in the field. So for the last one, please, I want to show it to you, the liquefaction on the ground. This is, if you pay attention to this one, based on the 2011 earthquake, we have a shaking on the ground, as you can see. And after 40 seconds, we can sand boiling on the ground surface after 40 seconds. So this is the shaking. And after that, poor water pressure builds up, and after 100 pure water pressure builds up, you can see the sand boiling and water comes out of the ground.
Ha, tamam, görelim.
Right there, the sand boiling. Okay, next slide. So this is the picture been taken in the 2013 in the Boğaziçi University from the conference in honor of Professor Kenji Ishihara. Again, thank you for Professor Huriye Bilsa and Professor Ishihara for your support and your supervision. Thank you very much.